Welcome back to the podcast, Yves. We're diving deeper into Python infrastructure for algorithmic trading, specifically the chapter on deployment. It's a crucial topic, and this section highlights the complexities involved. So, laying the groundwork is essential for smooth trading.
Absolutely, Matthew. Deploying Python code, even for simple tasks, can be surprisingly tricky. The chunk we're discussing emphasizes that it's not as straightforward as you might initially think. It points out the variety of Python versions, like CPython, Jython, IronPython, PyPy. And then, there's the eternal Python 2 versus 3.8 debate.
Right. It's a jungle out there. So, you're saying that even choosing a specific Python version introduces initial hurdles?
Exactly. CPython 3.8 is highlighted as the focus, and this decision is driven by popularity, and I would assume the community support for that version. But that's just the first step. The challenges extend beyond simply picking the interpreter.
Absolutely. The document also emphasizes the standard library versus optional packages, right?
Yes, the standard library includes basic tools, but for algorithmic trading, we need specialized libraries. The chunk stresses the need to install these packages separately, and there's a vast number of them, which is the real complication.
So, hundreds of packages. That's overwhelming. What are the practical implications of this massive dependency network?
Well, the document highlights the challenges of compiling these non-standard packages. There are dependency issues to consider, operating system-specific requirements, and maintaining version consistency over time. Imagine having to manage the versions of all these different libraries.
And what about updates and upgrades?
Updates and upgrades to certain packages can trigger the need to recompile many other packages, creating a cascading effect. And changing or replacing one package might cause problems in others. The entire system is tightly interconnected.
Makes perfect sense. That leads nicely into the discussion of package and virtual environment managers. What solutions does this document suggest?
The chapter recommends using package managers like pip or conda to handle installing, updating, and removing packages. Crucially, they help maintain version consistency. Also, virtual environment managers like virtualenv or conda allow users to manage multiple Python installations simultaneously, which is super important for testing different packages or versions.
So, virtual environments are a way to isolate projects and avoid conflicts?
Precisely. Virtual environments create isolated spaces for your projects, preventing problems that arise when different projects have conflicting package versions.
And how about Docker containers?
Docker containers package up your entire environment, the operating system, Python installation, and all the necessary libraries, into a single unit. This allows you to reproduce your environment consistently across different machines, even in the cloud.
This makes deployment much simpler. And finally, cloud instances?
Cloud instances offer high availability, security, and performance that are crucial for financial applications. You pay only for the resources used, and they're readily available on demand, which is crucial for scaling and flexibility.
So, Yves, we're diving deeper into setting up our Python environments for algorithmic trading. You mentioned Conda earlier. Now, you're saying mini Conda is a good approach, right?
Yeah, absolutely. Conda, by itself, is a powerful package manager, but mini Conda is often the preferred method for getting started. It's a streamlined way to install Conda, and more importantly, it gives you a minimal Python distribution.
Minimal? What does that practically mean?
Well, it means it doesn't come with a lot of extra packages. You're not cluttering your system with things you might not need immediately. Think of it like installing just the core tools you need in a workshop, the hammer, saw, and screwdriver, without all the extra gadgets. That way, you don't have conflicts later on. It makes managing your environment much smoother.
So, it's kind of like a lightweight version of the full Python distribution?
Exactly. You get Conda, which is essential for managing dependencies and creating virtual environments, along with a very lean Python interpreter.
Okay, so why is this a good thing for algorithmic trading?
It means less potential for conflicts, especially when you start mixing different packages for your trading strategy and libraries for analysis. Using mini Conda, you're more in control. You can have several separate environments for different projects or even different versions of libraries. This helps avoid compatibility issues and keeps your workflow organized.
So, if I'm setting up my trading environment, it's beneficial to install mini Conda first?
Definitely. You'll have a controlled and isolated environment to build your strategy within, right from the start. You avoid compatibility problems that could arise from pre-installed Python versions or conflicting libraries. It's a best practice, especially for more advanced projects.
Great. And as you mentioned, we can create isolated virtual environments, which was a topic in the previous chunk. How exactly does that further help with project management?
By creating separate virtual environments, you keep your projects isolated. Let's say you have one project relying on a specific version of NumPy, and another that requires a newer version. Using virtual environments, you can install different versions of libraries in each environment. You're no longer locked into one version. You can choose the precise dependencies needed for each project.
No conflicts, no headaches.
So, it's all about avoiding the potential chaos of conflicts. That makes total sense. Thanks for clarifying this, Yves. Welcome back to the podcast, Yves. We're diving deeper into installing Miniconda, a crucial step for anyone working with Python for algorithmic trading. Can you walk us through the process, focusing on the Docker container setup?
Sure, Matthew. So, we're using a Docker container running Ubuntu. This isolates our environment, preventing conflicts with our host system. The docker run command sets up the container and mounts the pyalgo host directory inside. Critically, this pyalgo parameter ensures the container uses that host name. It's like having a dedicated workspace for our Python and trading algorithms, which is very important.
Okay, that makes sense. Then, you're updating and upgrading the essential packages like GCC and will get for building and downloading Miniconda, right?
Exactly. apt-get update checks for package updates, apt-get upgrade y automatically applies them, and apt-get install y GCC get installs the essential compilers, GCC, and file downloader get. These are fundamental tools for compiling code and fetching files from the internet.
Right. Then comes the get command to download the Miniconda installer. Can you elaborate on that, especially the part about the URL?
The URL, https://repo.anaconda.com/miniconda/miniconda3 latest Linux, x86_64 specifies the location of the latest Linux 64-bit Miniconda installer for Python 3.8. It's essential to get the correct architecture, like x86_64, matching your system to avoid compatibility issues. This avoids any errors in the Python installation process.
So, miniconda.sh saves the downloaded installer as a local file. Then we execute the installer with bash miniconda.sh. What happens next?
That initiates the Miniconda installer. You see a welcome message and, importantly, are presented with the license agreement. Pressing enter moves to the next step, where you need to respond yes to accept the terms.
How crucial is that licensing agreement? And what if you didn't respond yes?
It's crucial because you need to agree to the terms to use the software legally. Failing to do so will prevent you from installing the package. The installer then prompts you for the installation directory, which by default is /root/miniconda3. You can modify this if needed.
What happens after we confirm the location?
The installation starts, downloading and installing the necessary packages. Then you're prompted to allow conda to initialize by running conda init. This adds the Miniconda bin directory to your path environment variable. This is so your system can find the conda commands.
So, you were saying the conda init step configures the system to recognize the conda installation?
Yes, you must execute conda init to ensure conda's commands are available system-wide. This enables you to use conda commands from your terminal easily.
Finally, there's an update step and adding the path to the /.bashik file. Why these extra steps?
Updating conda ensures you have the latest versions of the packages, often containing bug fixes and performance improvements. Appending the conda.sh path to your shell configuration file like debashik makes conda commands available in new terminals.
So, now Python and conda are installed. How do we verify this?
We open a new terminal, type Python, and it should launch the Python interpreter. We can also verify that conda commands work.
Welcome back to the podcast, Yves. We're diving deeper into Python for algorithmic trading, and today's focus is on using conda for package management. So, conda, it's a powerful tool, but what are its key benefits in this context?
Absolutely, Matthew. Conda is a fantastic package and environment manager, especially crucial for algorithmic trading where you often need specific versions of libraries and tools. It essentially handles all the dependencies, installing packages and managing the versions, in a way that avoids conflicts. You wouldn't have to worry about different package versions clashing with each other or trying to figure out compatibility problems.
That makes a lot of sense. So, installing a package like NumPy, for instance, you mentioned it's just a single command. Can you elaborate on the efficiency of that?
Right, Conda install NumPy. It's remarkably streamlined. And it's not just installing NumPy, it handles the dependencies, like the Intel Math Kernel Library, MKL, automatically. This is where it really shines. If you're on an Intel machine, the process efficiently installs the optimized MKL library. This optimization is super important. It dramatically speeds up numerical computations, which are vital in algorithmic trading.
So, it pre-integrates the necessary components, right? That's crucial for performance. What about installing multiple packages at once?
Exactly. If you need multiple libraries like Ipython, Matplotlib, Pandas, Pytables, scikit-learn and SciPy, you can install them all together using conda install y. The y flag is a time saver. It automatically answers yes to any prompts.
Excellent point. And what happens when a package needs to be removed or updated?
For removing, you just use conda remove. Conda handles dependency management there too. For updating, you can do conda update or conda update conda to update the package manager itself.
Okay, I see the workflow is smooth. This simplifies the process considerably. Let's talk about the practical example you cited, using Ipython and NumPy to generate random numbers. What's the key takeaway there?
The key takeaway is that once you have the environment set up correctly using conda, you can seamlessly integrate Python's core libraries and tools into your algorithmic trading strategies. The example of generating random numbers with np.random standard_normal 5-4 is very straightforward, as NumPy has this powerful ability. You need the packages installed, properly managed, and ready for use.
So, the whole process from installation to running code becomes easier and more reliable. That's significant. Concisely, what's the biggest advantage in using conda from an algorithmic trader's perspective?
From an algorithmic trading perspective, it's speed and reliability. Conda simplifies environment management, meaning your trading code can be more easily replicated across different machines and environments without needing to reproduce the entire dependency setup each time. You can be confident that your environment is properly configured without worrying about compatibility issues. This efficiency directly translates into less time spent troubleshooting and more time focused on strategy development and testing.
Welcome back to the show, Yves. We're diving deeper into Python for algorithmic trading, and today we're focusing on conda, a powerful virtual environment manager. Can you give our listeners a quick overview of what conda is and why it's important in this context?
Sure, Matthew. Conda is essentially a package and environment manager, specifically designed for Python. It's super useful because, well, in algorithmic trading, you often have different Python versions and libraries you need for different strategies or projects. Conda lets you isolate those environments, so you can have Python 3.8 for one project and Python 2.7 for another, and those installations won't conflict. It's like having separate contained boxes for your projects, keeping everything neat and organized.
Right, so it's about isolating dependencies. Can you explain how conda creates and manages these virtual environments?
Absolutely. It uses commands like conda create, name $environment_name. That creates a new virtual environment with a name you specify. For instance, conda create, name py27 python equals 2.7 creates an environment called py27 specifically using Python 2.7. Then you activate it with conda activate $environment_name. So conda activate py27 in our example. That changes your command prompt to show you're working within that environment.
So you're essentially switching between different Python versions, and the installation doesn't get corrupted or affected by this, right?
Exactly. The beauty is that the default Python installation on your machine is completely unaffected. You can have any number of these isolated environments active or inactive, without compromising the others. Crucially, you can also deactivate them with conda deactivate, going back to your base environment.
Okay, So, creating the environment, activating it, deactivating it. What about the actual installation of packages like IPython?
You install packages within the activated environment using commands like pip install ipython. In the example, they use pip install ipython in the py27 environment. A key takeaway here is the importance of activating the appropriate environment before installing packages. That's fundamental to Conda's organization.
You mentioned Python 2.7 is now outdated, but the example shows using it. What's the reason for that? And what are the implications of keeping it in a separate environment?
Well, many older trading strategies or codebases still rely on Python 2.7. Using Conda, you can keep the old code running, even though support has ended. Keeping it in a separate environment is crucial because it completely isolates this legacy code, preventing conflicts with more modern Python and packages. You can test and maintain existing Python 2.7 strategies and libraries.
And if you need to share or replicate this environment across machines, how would you do it?
You use the conda env export command, often followed by $file_name to export the environment to a file, like base.yml in the example. That file contains the list of packages and versions. And if you want to reproduce it on another machine with conda, you can use conda env create $file_name. However, be mindful that the exported file often includes build versions, making it OS-specific.
Got it. You can avoid OS-dependent issues by adding the no builds flag. Now, if you want to get rid of an environment, how does Conda handle that?
You use conda env remove, name $environment_name. For example, conda env remove npy27 will remove the py27 environment, provided it's deactivated. That command deletes all the packages within the environment. It's crucial to deactivate first, otherwise, you could have issues.
This all sounds incredibly useful for maintaining a structured and robust project environment in Python algorithmic trading, UVs. Thanks for clarifying all that.
My plaisir, messieurs. It's a powerful tool to have in your arsenal.
Welcome back to the podcast, UVs. We were just talking about Docker containers, and it's fascinating how they're transforming the way we build and deploy software, especially Python applications. Can you tell us a bit more about what a Docker container actually is?
Sure, Matthew. Think of a Docker container as a self-contained package. It's not just the code, but everything the application needs to run: the operating system, the runtime environment, like Python, system tools, and all the necessary libraries. So, you're essentially packaging up everything an application needs to work perfectly, independent of the host system.
So, it's like a virtual machine, but lighter?
Exactly. It's more lightweight than a full virtual machine. A virtual machine creates a whole new virtual environment, which is a bit of an overhead. A Docker container uses the host operating system's kernel, so it's more efficient. This is crucial, especially when scaling up. You can run tons of containers on a single machine without the performance issues of running many VMs.
And how does this relate to Python for algorithmic trading?
Well, the portability is huge. Imagine you have a Python algorithmic trading strategy running perfectly on your local machine with Windows. Using Docker, you can create a container that includes the necessary Python libraries, the trading engine, and any other dependencies. Then you can easily deploy this container to a cloud server running Linux, for instance, or even on a different machine. The exact same environment will run flawlessly on these different systems.
That's brilliant. So, the operating system, Python interpreter, and libraries are all packed into one container?
Precisely. And this is important for reproducibility. If your trading strategy requires a specific version of NumPy or pandas, you just include that version in the container. So no more "it worked on my machine" headaches.
So, it's really about consistency, portability, and reliability across different platforms and environments, right? Why is that crucial in a trading environment?
Absolutely. If your trading strategy relies on specialized algorithms and libraries, and it's not consistent across different environments, it introduces a whole host of potential problems. Using Docker ensures that your trading application always functions the same way, no matter where it's run, ensuring high-performance consistency and reliability.
That makes total sense. So, Docker lets you create a standard, repeatable environment for development, testing, and deployment. That's really powerful. Any closing thoughts on Docker containers' advantages for algorithmic trading?
Yeah, it's not just about portability. It significantly streamlines deployment and scaling. You can easily replicate your environments across a cloud infrastructure. Deploying and scaling your trading applications becomes much simpler. Also, the container image is a very handy way to share your trading environments and configurations with your team, which enhances collaboration.
Okay, Yves, we're diving deeper into Docker now. So, we've established that Docker images are like Python classes, right? Can you elaborate on what that analogy actually means in a practical sense for algorithmic trading?
Absolutely, Matthew. Think of a Docker image as the blueprint for a trading strategy. It defines all the necessary components, libraries, and dependencies, just like a Python class defines the attributes and methods of an object. It doesn't have any actual data yet, just the structure.
Right, so it's like the code itself, but not running?
Exactly. It's the recipe. It tells Docker how to create a container that can execute the strategy. And that's where the container part comes in.
So, a container is like an instance of a class?
Precisely. A container is a running instance of that image. It's the actual trading bot, the live implementation of the strategy, using the resources defined in the image. It has state, it does the work. Crucially, the container is isolated, which means it runs independently from the other containers and from the host operating system.
That isolation is key for algorithmic trading, isn't it?
Absolutely. You don't want one strategy interfering with another, or a bad strategy crashing the entire system. Docker's isolation is super important for preventing issues. And the beauty is that each container is portable. You package the image, ship it anywhere, and you know the environment will be exactly the same.
So, you're saying that a Docker image is basically a consistent environment for running the code. How does that consistent environment tie into the whole concept of shipping software?
That's the whole point. The Docker image is the standardized package. It defines everything required for a specific trading strategy, from the operating system to all the packages and libraries. It's like having a standardized shipping container for goods. The goods are your trading code, and the container makes sure they arrive intact and ready to use in different locations. So you know that wherever you deploy it, it's going to work as expected.
So, the image itself doesn't change? It's immutable.
That's right. Once the image is built, it's fixed. You can't change it in the middle of a trade execution. You create a new image if you need to update something. That's why it's built in layers, like building a house, where each layer builds upon the previous one. This makes the building process efficient and manageable.
I see. So, the layers in an image make it easy to update and maintain the software?
Yes, updating only the necessary layers means you can deploy updates without the risk of breaking compatibility or integrity. It speeds up development and deployment. The image's immutability makes updating a bit safer and cleaner. The changes that are required are simply packaged into a new image.
Excellent. So, each layer represents a new development or dependency.
Exactly. This layering method also improves efficiency. It allows for easier troubleshooting and maintenance as well, since you can trace issues to specific layers in the image and target the source of the problem.
Welcome back to the show, Eve. We're diving deeper into building Docker images for Python, specifically for algorithmic trading. So, we're looking at this bash script and the Docker file. Can you walk us through the key elements of the bash script?
Sure, Matthew. This bash script, basically handles the installation of everything we need. It's structured into 3 main sections. First up is the Linux housekeeping. This is crucial because, well, you want a clean, consistent environment. Think updating the package index, upgrading existing packages, and then cleaning it up again afterward. It's like preparing your workspace before starting your coding session.
So, apt-get update and apt-get upgrade. Why? Tell us more about those.
apt-get update refreshes the list of available packages. apt-get upgrade, automatically upgrades any packages that are out of date. This makes sure we're running the latest versions, potentially with bug fixes and performance improvements. The Y option means yes to all prompts, making the process smoother and faster. Then there's a cleanup step, apt-get clean, which removes old package information. It's like decluttering your system.
Got it. And then the second part is installing Miniconda. Can you elaborate on why Miniconda? And what advantages does it offer for this scenario?
Yeah, Miniconda is a smaller, more streamlined version of Anaconda. It focuses on just the packages you need. For our Python work, we only need certain libraries. With Miniconda, we install only those, making our Docker image lighter. This, ultimately translates to faster build times and less storage consumption, particularly useful when deploying on limited resources, like cloud servers or smaller local machines.
Right. And the third part installs Python libraries like pandas and IPython. Why those specific packages?
Pandas is fantastic for data manipulation, which is fundamental in algorithmic trading. And IPython, that's an interactive Python shell. It makes development and testing much more intuitive and manageable. You can quickly experiment, try out different code snippets, and view the results directly. It's essential for fast prototyping and debugging in a contained environment.
Now, let's shift to the Docker file. You mentioned a install.sh script being used within it. Can you outline the Docker file's role in the image building process?
This Docker file essentially encapsulates the steps to create the final image. The from Ubuntu latest line specifies the base image, the latest version of Ubuntu. The add install sh copies the bash script into the image. The run chmod u plus x/install sh makes the script executable. Then run/install sh executes the script, doing all the installation work. And finally, env path sets the path for our new Miniconda environment to be available to any application or process run later in the container. cmd ipython specifies that IPython should run as the command when the container is started, making it immediately useful.
So, essentially, the Docker file acts as an automated recipe for building a containerized environment. This isolates all our tools and dependencies, making it easier to deploy, maintain, and reproduce our trading algorithms across different environments. That sounds incredibly useful. It gives us the ability to deploy algos without having environment configuration headaches.
Exactly, Matthew. It's a great way to ensure consistency and efficiency. You package everything you need neatly in an image, so you always get the same behavior, whether on your laptop, a server, or in the cloud.
Welcome back to the show, Yves. We're diving deeper into setting up Python infrastructure on cloud instances, specifically DigitalOcean droplets. So, we're talking about using these cloud instances for our Python algorithmic trading projects. This chunk gives us the high-level picture of the tools and scripts involved, right?
Absolutely, Matthew. We're essentially building a whole Python development environment on a virtual machine in the cloud. Think of it as having a powerful, dedicated computer that's accessible remotely, which is incredibly useful for trading algorithms.
Right, so we're not just running code on our local machines. This gives us flexibility and scalability.
Exactly. We're creating a virtual environment where we install Python, JupyterLab, and all the necessary libraries like NumPy and pandas. And crucially, this whole process is being set up with security in mind, with SSL encryption and password protection for JupyterLab. This is important for, keeping our trading systems safe.
You mentioned JupyterLab. Can you elaborate on its usefulness? It's not just a notebook, is it?
No, JupyterLab is a more comprehensive environment. While Jupyter Notebook is part of it, it offers a lot more. You've got a terminal, a file manager, an editor, and even a Python console, all within a web browser. So you can manage your files, run code, and debug without needing to log into the server via SSH. It streamlines the development workflow significantly, especially when you're working on a team or collaborating remotely.
That sounds efficient. So, we'll have a web-based interface for all this. What about these scripts you mentioned? The server setup script, the Python and Jupyter installation script, are they crucial?
Absolutely crucial. The server setup script, essentially orchestrates everything, ensuring all the necessary components are properly deployed and configured on the droplet. The Python and Jupyter installation script is where the actual Python installation and the installation of JupyterLab, plus associated packages, happen automatically. This is key for automation and consistency across deployments.
Interesting. So, we have a script to install the environment and one to orchestrate everything. That makes sense. And you said there's a configuration file for JupyterLab?
Yeah, the Jupyter Notebook configuration file is used to customize the server, like setting up password protection for the JupyterLab interface. This is a standard practice for security. Security is paramount for any trading system, so configuring this is fundamental.
And the RSA public and private keys? That's for the SSL encryption?
Precisely. These are essential for secure communication between your computer and the Jupyter Lab server running on the droplet. The encryption ensures that data transmitted between the two is secure and prevents unauthorized access.
Great. So, we're setting up a fully functional, secure Python environment on a cloud instance, controlled via scripts and configuration files. This is a powerful setup for algorithmic trading. Thanks for the insights, Yves.
My pleasure, Matthew. We'll dive into the specifics of these scripts and files in the next section. But for now, the big takeaway is automation and security.
All right, Yves, so we're diving into setting up a secure connection for our Jupyter Lab server. This chunk talks about generating those crucial RSA keys. Can you walk us through the process and why it's essential for a secure connection?
Sure, Matthew. We're generating an SSL certificate, which is fundamental for secure communication over HTTPS. Think of it as a digital passport, verifying the identity of the server. It uses RSA encryption, which is a widely used asymmetric cryptographic algorithm. Basically, it uses a pair of keys, a public key and a private key.
Okay, so we need both public and private keys? How do we get those?
Exactly. The code snippet shows using OPencil. It's a command line tool for various cryptographic operations, including generating these key pairs.
The command OPencil x509 nodes des 365 nuclear 2048 Key out meistert. P-misse key. Let's break it down.
X509 tells OpenSSL to create an X.509 certificate, a standard format for digital certificates. Nodes is important. It means the private key won't be protected by a password. Days 365 sets the validity period for 365 days. New key RSA 2048 specifies that we're creating a 2048-bit RSA key pair, a significant strength for security. Key tells OpenSSL to save the private key to the file myki.key. Out mysert.pem saves the certificate to mysert.pem.
So, that command generates the key pair. But what about the information it prompts us for? Like the country, state, locality, etc.? What are those fields?
Those are part of the distinguished name, DN, essentially the identity information embedded in the certificate. You can leave some fields blank, denoted by a period. It's crucial to fill in accurate information, particularly the common name, CN, which identifies the server. In this case, it's the Jupyter Lab server.
The other fields, country, state, organization, give a sense of the certificate's origin.
So, accuracy is vital. And what happens if we don't copy those files, myki.key and mysert.pem, to the server?
Well, the server won't be able to authenticate itself securely, as it will lack the necessary cryptographic material. You have to place these files in the appropriate location on the Jupyter Lab server, and reference them in the Jupyter Notebook configuration file, as mentioned. This configuration file tells Jupyter Lab how to use the certificate. Without those steps, you can't have a secure connection.
Excellent, Yves. So, the certificate is our way to ensure our connection is encrypted, and these keys are vital to making that encryption work. That's all very helpful for understanding the setup process. Thanks again. Welcome back to the show, Yves. We're diving deeper into configuring Jupyter Notebooks for secure cloud deployments. We've just seen the need for password protection and SSL encryption. Can you explain why this is so crucial for a cloud-based Jupyter Lab?
Absolutely, Matthew. Jupyter Lab is a powerful tool, but when it's accessible over the internet, like in a cloud environment, it opens up security vulnerabilities. Think of it like leaving your front door unlocked. Anyone with the right tools could potentially access and even manipulate your data. Password protection, along with SSL encryption, are essential first lines of defense.
Okay, so password protection is key. Let's unpack that. The example shows a function password, which creates a password hash. Can you explain what a password hash is and why we don't store the plain text password directly?
Sure. A password hash is essentially a one-way function that takes your password and transforms it into a unique, seemingly random string. Crucially, it's almost impossible to reverse engineer the original password from the hash. If someone were to somehow gain access to the configuration file with the hash, they wouldn't be able to simply read your password. That's a massive security boost. Storing the plain text password directly would be a significant security risk.
Right, I understand that. So, the password, Jupiter, part of the example, is that just a simple call to the function?
Exactly. You're passing the password string, Jupiter, to the password function. The function then generates the hash, the long string you saw in the output. This hash is what you need to replace the placeholder in the configuration file.
And the configuration file itself? What's the significance of placing the hash there, rather than, say, in a separate file?
Well, you're essentially protecting the password itself from direct access. This is done to prevent anyone from casually accessing and potentially obtaining the password. The configuration file is read by Jupiter when it starts up, checking if the hashed password matches the attempt. The password isn't sitting out there exposed. Placing it directly in the configuration file is more efficient as it's already part of the authentication process.
Excellent. And in the config file, there's this crucial line, .notebookapp.password equals. How do we ensure that this hash corresponds to the correct password?
That's the whole point of the hash. It's tied uniquely to that password. When a user logs in, Jupiter uses the same function password to create a hash of the entered password. Then, it compares that hash with the hash stored in the configuration file. If they match, the user is authorized. If not, access is denied.
Great, that clarifies the crucial role of hashes. Now, regarding SSL encryption, what practical measures does that entail in this scenario?
SSL encryption ensures that all communication between your client, like a web browser, and the Jupiter Lab server is encrypted. This prevents eavesdropping and ensures data integrity. The cert file and key file settings in the config file are crucial for that. You need to create a certificate and key pair, the mycert.pem and mykey.key files, for example. This is a fundamental part of the setup for secure cloud deployments.
Thanks, Eve. That was a great overview. We've covered password protection and SSL encryption, setting the stage for securing your cloud-based Jupyter notebook. Is there anything else we should consider when deploying a Jupyter server?
Well, definitely, Matthew. There are additional security measures, for example, restricting access to specific IP addresses, limiting the users who can connect, monitoring access logs, to name a few. The security level should align with the sensitivity of the data.
Welcome back to the show, Eve. We're diving deeper into this Python installation script for algorithmic trading. This script, it's quite comprehensive, isn't it? It's handling a lot more than just the core Python setup.
Absolutely, Matthew. This script is designed to set up a complete environment for algorithmic trading, including installing the necessary Python libraries and tools, and crucially, launching JupyterLab. It's not just about getting Python running, it's about creating a robust development platform.
Right. So, let's break down these steps. First, we've got this Linux system tool installation. Why are these essential?
Well, you need basic utilities like Build Essential, Git, Screen, Top, Vim, and Wget. These tools are fundamental for compilation, version control, managing terminal sessions, monitoring processes, text editing, and downloading files. Think of them as the underlying infrastructure for any development work. Without these, you might encounter trouble compiling libraries or managing your code efficiently.
Okay, I see. And then we're installing Miniconda. Why not just use pip?
Miniconda, or Anaconda, offers a pre-packaged environment with many important libraries, all managed in a consistent manner. The script starts by installing Miniconda, which is a Python distribution that includes a package manager called Conda. Pip, while powerful, can sometimes lead to conflicts with package versions and dependencies, making project reproducibility more challenging. Miniconda helps manage dependencies better and offers a clearer structure for your libraries and their versions within a project, making sure things work as expected across different systems and deployments.
Interesting. And the script prepend the Miniconda path in the current session and the shell config. Why is that critical?
That's important for making the conda and pip commands available from your terminal. You have to update your shell environment variables to find and utilize them after installing the package manager.
Got it. Now, the next section covers installing a bunch of Python libraries. Can you highlight some crucial ones?
Definitely. You've got Jupyter and JupyTerLab for interactive data analysis and development in the browser. Crucially, NumPy, pandas, SciPy, Matplotlib, and Seaborn are fundamental for numerical computing, data manipulation, scientific computing, and visualization, respectively. Then there's Pytable's for HDF5, which is frequently used for large datasets, Quandl for accessing financial data, scikit-learn for machine learning, OpenPixel, XLRD, XLW for working with Excel files, PyYAML for managing YAML configurations, and Plotly, Cufflinks, and TensorFlow/Keras for more advanced visualization and deep learning tools.
That's a significant toolkit. And finally, we're starting the JupyterLab server. Why is that the preferred way to run these notebooks?
JupyterLab provides an interactive environment to run and develop your Python code. You can easily test and modify code segments, visualize data, and run experiments, all in a dynamic, iterative way. This interactive aspect is key to the Python for algorithmic trading workflow. The script uses JupyterLab and the ampersand and in the command is critical for running JupyterLab in the background. This allows your script to continue executing other tasks without halting.
So, this script doesn't just set up Python, it builds a complete workbench for algorithmic trading, right? From the core language, to the essential libraries, to the interactive development environment.
Exactly. It's a streamlined approach to setting up the necessary components for algorithmic trading in Python.
Thanks, Eve, for clarifying all of these details. This helps us understand the importance of this script for anyone embarking on algorithmic trading using Python. Welcome back to the podcast, Eve. We're diving deeper into setting up a droplet for algorithmic trading using Python. So, this script we're looking at, it's pretty concise, isn't it?
Yeah, it's designed to be streamlined. The key here is efficiency. This script primarily handles the file transfer and then kicks off the installation process.
Right. Could you unpack that a bit more? What are the crucial steps this script takes specifically regarding file transfer?
Well, it uses SCP to copy the necessary files, including install sh, your security certificate, mysert.pem, the key, mikey.key, and configuration files like Jupyter_notebook_config.py to the droplet. Crucially, it uses the droplet's IP address as a parameter, which is extremely important for targeting the correct machine.
So, the IP address is a command line argument? That's a powerful way to make it adaptable for different droplets.
Absolutely. This is how scripts like these are highly reusable. You don't have to hardcode the IP address in the script itself. You simply pass the correct droplet IP to the script as input.
That makes sense. Then it uses SSH to execute install.sh. What's inside that install.sh script doing?
That's the heart of the installation. It's responsible for installing the necessary Python packages, setting up the Jupyter Notebook environment, and finally, launching the JupyterLab server. The script usually handles environment configuration, package dependencies, and starting the server.
So, the key steps are receiving the IP, copying the required files, and initiating the installation process on the droplet, which then launches the Jupyter server. What are some important things to consider about the installation process on the droplet itself?
Well, you need to ensure that the droplet has the necessary packages to execute install sh. For example, you should install or pre-install apt pip on the system, otherwise install sh might fail. You also need to remember to allocate sufficient resources for the server to handle the Python packages that get installed. If the server doesn't have enough memory or CPU, it could take a while for the server to come up. And if the server is too weak, it might crash while the packages are being downloaded.
Great insights, Eve. So, what about the size and configuration of the droplet itself? It mentions a specific setup in the example. Are there any important considerations for selecting the right droplet size?
Yes, the example specifies a 2-core, 2 GB RAM droplet, but depending on the complexity of your algorithms and the amount of data you're working with, you might need to adjust the resource allocation. A larger droplet is recommended for more intense calculations in more demanding trading strategies.
Thanks, Eve. That's incredibly helpful. We've now covered the entire droplet setup process. It's clear that careful consideration of the droplet resources and the install.sh scripts tasks is vital for a smooth deployment. Okay, Yves, we've established Python as the go-to language for algorithmic trading. But you mentioned deployment can be tricky. Can you unpack that a bit more? What are the specific hurdles?
Yeah, absolutely. Deploying Python applications, especially for something like algorithmic trading, can be a real headache. You've got your Python code, your libraries, and then you need a robust environment that's consistent and reliable. You don't want to have different versions of Python or packages leading to errors when you run the code on a different machine or, in a different cloud environment.
So, what tools can help us smooth out that process?
Well, there are some excellent tools available now. OANDA, for example, is a lifesaver for managing Python packages. It essentially creates a self-contained environment with all the necessary packages for your application. That isolates your dependencies, making sure that your code will run the same way everywhere. It's incredibly useful for reproducible results.
And Docker containers? What's the benefit there in this context?
Docker containers go a step further by encapsulating the entire runtime environment. Think of it as a complete package including not just your Python code and libraries, but also operating system dependencies and even the necessary system utilities. So you're effectively creating a portable, reproducible execution environment that's super consistent. It's like a tiny self-sufficient computer ready to run your code wherever you want.
That sounds fantastic. So, this whole container approach, it's like an isolated sandbox?
Exactly. You can run your trading algorithm inside that isolated container, which prevents any potential conflicts with the host system. And you're not worrying about whether the system you're running it on has the right configuration or permissions, which can be massive headaches.
And cloud providers like DigitalOcean come into play here, right?
Absolutely. Cloud providers give you ready-made compute resources that you can provision in minutes, often billed on an hourly basis. You can spin up a server, install your Docker containers, and deploy your Python applications without needing to manage physical hardware. It's incredibly convenient and cost-effective, especially if you're only running your algorithm part-time.
So, combining all these tools, Python 3.8, OANDA, Docker, cloud servers, and Jupyter Notebook, you basically have a fully managed environment for algorithmic trading applications ready to use?
Precisely. You get a professional setup, a robust, reproducible, and manageable environment that scales to your needs, essentially, all the components for a successful algorithmic trading project. It's much easier to manage and deploy than struggling with a traditional setup.